We're very pleased to have Dr. Catherine Hayhoe from Texas Tech. She flew in this morning, and I'm feeling pretty good that she arrived. It's the things you can't control that really worry you the most. So we're very, very happy to have her here and grateful that she agreed to come and talk to us. She's an associate professor in the Department of Political Science and director of the Climate Science Center at Texas Tech University, which is part of the Department of Interior South Central Climate Science Center, the same center we've been talking about here. Her research focuses on establishing a scientific basis for assessing the regional to local scale impacts of climate change on human systems and the natural environment. Catherine has a Bachelor of Science in Physics and Astronomy from the University of Toronto and a Master's of Science and PhD in Atmospheric Science from the University of Illinois at Urbana-Champaign. She has been extremely active in her field and the recipient of numerous awards, and we're very pleased to have her here today. So with that, Catherine.
Thank you for that kind introduction, Jerry. It's such a pleasure to be here, and I don't think it's a coincidence that here at OU and at Texas Tech, we now co-host two centers with very similar foci, shall I say. We are partners in the Climate Science Center, which is our regional climate science center that represents our South Central region, and then now we are also partners in the Southern Plains Transportation Center. So I appreciate the chance to meet with you here today and to talk about some of the work we do related to climate variability and long-term trends in our region. So my talk today has 4 parts. And the first part, I think, that we need to start with is acknowledging what we all know, and that is that we live in an unusually challenging part of the country when it comes to designing infrastructure. Now, in Lubbock, where Texas Tech is, most people the past 4 years or so have been talking about drought. But last week, that is what it looked like on the Marcia Sharp Freeway in Texas Tech. That is our stadium up there. Some enterprising students took advantage of the situation. I don't think they were going to class, though, somehow. So little do you know that when you're in Lubbock and you're designing roads and highways, they're actually going to be used for boats and jet skis as well. The last few years, though, our climate has looked a lot more like this. Across West Texas, at least, most of our lakes are still at record low levels. Some things are not even called lakes anymore because there's nothing left in them. We have seen wildfires that create significant damage to infrastructure and pavement. This is the Possum Kingdom wildfire of a number of years ago, and you can still see the scars of this on the roads in the region. We have very challenging types of weather events. This is not just a dust storm, but a haboob. This is the haboob that swept through a couple of years ago. It was a 500-foot wall of dust. When it hit, you couldn't go anywhere for over an hour, and that's with lights and with street lights. I have to say that I was actually not in Lubbock for this event. I was at a Climate Science Center meeting in Denver. But I was flying out on United on the one direct flight we have to get out of Lubbock to Denver. We do have a direct flight. And I got a call that morning at like 5 in the morning saying, your direct flight has been canceled, but if you can get to the airport an hour and a half early, we'll put you on a flight through Houston. So that's not exactly the kind of call you want to get at 5 in the morning. So you fly out of the door with your bunny slippers on, and I got to the airport, and I was in such a hurry, I forgot to close my car window after I got the parking ticket. Yes. When I came back, let's just put it this way, that parking ticket was long gone, as was all the mail that used to be sitting in the front seat. I could not turn on the vents because half the dust storm would come out the vents. So that was an interesting experience of this. But we also have to recognize that literally the year before the haboob, this is what our stadium looked like. So one of the few claims to fame that we actually have in Lubbock is that we actually won the toughest weather tournament last year. We beat out Fairbanks, Alaska, but I hear they are considering Norman for next year. And we haven't even talked about tornadoes. We haven't talked about hailstorms. We haven't mentioned ice storms. I was in Dallas for the ice storm this past winter. Let me just say nobody knows how to drive on ice there, and I've never seen ice like that before in my life, and I'm from Canada. And even hurricanes. So doing the math for the Southern Plains, we have a substantial natural challenge in this part of the world. We are subject to almost every type of weather extreme you can imagine. That already poses a significant challenge for our infrastructure. But adding to that, we have human factors. We have the fact that we have rapidly growing cities. A number of the fastest growing cities in the US are located in our region. We have highly developed infrastructure. We have a strong car culture here. We actually never even had to own 2 cars until we moved to Texas. We always made do with one in Illinois, and when I lived in Canada, I actually had none. I had a boat and I had a canoe, no car. So we have a culture that is very dependent on personal transportation here. And we also, located where we are, have an enormous amount of transportation within and across our region. So this already creates significant challenges for developing and maintaining our infrastructure in this region. So the next question then, part 2, is, well, why does climate matter then? Here in a nutshell is why I believe that climate change matters to us. And there aren't going to be any pictures of any polar bears here. That's an infrastructure issue for up north. If the polar bear is sitting in the middle of the highway. Our society and our infrastructure is by and large built on the assumption that we can have extremes, we can have heat and cold, we can have wet and dry, we can have all kinds of weather extremes, but over longer time frames, 20, 50, 100 years, it all averages out. The 100-year flood from the last century will be the 100-year flood of the next century. The temperature extremes we've experienced over the last 30 years will be the same as we experience over the next 30 years. These are the assumptions that are built into our manuals. We partner with infrastructure engineers in the Northeast as part of a center called the ICNet, Infrastructure Climate Network. And one of our engineer partners actually brought their design standards one time to a meeting to show us ignorant climate scientists exactly what we were trying to deal with. It was a binder, and I'm sure some of you have seen it. It was a binder this thick. And they're like, you're trying to change our design standards based on climate? It was then that we realized what a big challenge we had in front of us. Because here's the problem. What if that assumption is no longer valid? What if we are still subject to the same patterns of natural variability and climate and weather extremes that we have always had here? But what if on top of that there is a long-term trend that is changing the risk of many of these events? An analogy that we often use in climate science is an analogy of 2 dice. We always have a chance of rolling a double 6. That double 6 could be the extreme heat that melts the asphalt. It could be the freak hail event or flood. We always have a chance of rolling that double 6. What climate change is doing is one by one it's taking those numbers and replacing some of the other numbers with 6s, so it is increasing the risk of certain types of events. And we'll see what those are. We know, looking across the U.S., that it is getting warmer. A lot of these are images from the U.S. National Climate Assessment that was released in May. They have a really good website. If you haven't seen it, you can download all the graphics in PowerPoint. What a novel idea. You can also click on a lot of interactive maps, and then you can actually get the report if you want. The U.S. as a whole is getting warmer, some places faster than others. But it's not just about our average temperature, it's also about our extremes. We are seeing an increase in extreme heat waves. And it's not just here in the U.S. In Australia, a year and a half ago, they had a heat wave so extreme they had to add a new color to their temperature map. That light purple there in the middle is 54 degrees Celsius, 129 degrees Fahrenheit. They had never had that before. And this is not just happening in Australia. We're seeing it around the world that our heat waves are becoming more frequent and more severe. We're also seeing more frequent heavy precipitation events. Now, I said precipitation very carefully because it isn't just about rain. What happens, and we were talking about this earlier in the presentation before the break, as the world warms, more water evaporates into the atmosphere. When a storm sweeps through, there is more water available for that storm to pick up and dump. If it is above freezing, it dumps it as rain. If it is below freezing, it dumps it as snow. And the news is, yes, climate is changing and the globe is warming, but it's still cold enough to snow across much of the U.S. So ironically, and this is one of the challenges with climate communication, ironically, a warmer planet could lead to stronger snowstorms. And we have some evidence that it may be in the Northeast. We also see that the ocean is warming, powering stronger storms. We are not seeing any more frequent hurricanes at all. We have no record of more frequent hurricanes. But what we are seeing, and what our models project for the future pretty consistently, is stronger hurricanes. On top of that, we know that sea level is rising, so when a hurricane does come, the storm surges are going to be higher because there's that much extra water involved. And if you look around the U.S., we see that on average, from 1980 to now, we typically have about 1 or 2 events a year that cost more than $1 billion in damages related to climate and weather. But over the past couple of years, we've been seeing more like 10 or 12 events per year. It's too early to get a definitive trend out of it, but we're definitely starting to see impacts that are hitting us in our wallet. Now again, why is Texas dark red there? It's because we get it all, don't we? We get the floods and the droughts, we get the heat waves and the ice storms. We get the hurricanes, we get the tornadoes and the hail. I mean, what is there that we don't get, honestly? So what do we need to know to start integrating this information with what we do? The most important information that we need is how climate and weather already affects our systems. And much of us, that information is already at our fingertips. In the city of Chicago, they're really worried about potholes. They know how many freeze-thaw cycles cause potholes. And if you've ever been in Chicago, anybody been in Chicago and driven over those potholes? Sometimes you feel like you're going to lose a wheel. We used to have a little Jetta when we lived near there, and I'm serious, I thought the wheels in the Jetta were coming off a few times going through the potholes. Other systems affected by climate include even things like tourism. People don't show up for outdoor festivals if it's too hot and humid. Our health is affected. We know how much rain it takes to flood our underpasses and our roads. In Lubbock, it's 3.5 inches in 1 hour. You know, the jet ski? That was what happened. Then let's connect these types of events to what weather or climate events cause these. A lot of our damages could be caused by wildfire. Further west of where we live, they could be caused by rapid snowmelt, or hurricanes, or heat waves. And here's the thing. For many purposes, we can stop here. All we need to know is the vulnerability of our system and in what direction those future stressors are changing. Are we going to have higher risk of extreme heat events? Are we going to have higher risk of heavy downpours? If the answer is yes, from the historical observations and the future projections, for some applications that's all we need. We can just stop. Right there, we have the information we need to plan, to make sure we're prepared for a different future. But for other applications, we need more. For example, what if we are designing a stormwater system? In Lubbock, we do not have a stormwater system. Or I should say we do. It's called the freeway. Say you're designing one that actually has real pipes in it that's designed to carry water. Well, then it makes a big difference. If I can go back to where we were here. There we go. It makes a big difference if you're designing a system that's supposed to last for 80 years, say. Are the frequency of extreme precipitation events going to increase by 50% over those 80 years? By 100%? Or by 200%? It makes a big difference in the width of the pipes. And the width of the pipes makes a big difference in terms of the cost. So for other applications, we need more information. It isn't enough to, where was I here? It isn't enough to stop right here and know the direction of the trend. We need quantitative information. How do we get this information? That's what I'm going to talk about next. We know that the future is uncertain. But we also know that if we assume climate is stable, we are going to get the wrong answer. If we go back to this and we use this as a guide to the future, we'll be okay in terms of the variability over 10 years, maybe over 20 years. But if we are designing or maintaining infrastructure over any time horizon longer than 10 or 20 years, and we leave this trend out of the picture, we are going to get the wrong answer. We are going to be designing infrastructure for a system or for conditions that it was not designed for. So that is why the future information is so important. But here's the deal. Why is climate changing? If climate is changing due to natural causes, then all we can really do is use historical observations as a guide to the future because it's all going to average out. Now, why am I getting into this whole idea of why climate is changing? I have to be honest, I was actually not sure whether I should talk about this here. I figured, hey, you know, Climate Science Center, everybody's on board, you know, this is just repeating the same old stuff. And then I got a review back from a paper that I submitted to the Transportation Research Board in August. I got a review back this morning. I read it on the plane. The editor was very careful to tell me that they had selected extremely high-quality reviewers to review our paper, which I appreciated. One of the reviews said, and I quote, "Why are you talking about human-induced climate change? Don't you know a lot of people don't agree with that?" And it is completely true. We have to acknowledge the fact, at least in Texas, that 6 out of 10 people do not agree with it, and a lot of those people are engineers. And some of them are scientists. So I think it's really important to distinguish here why we think climate is changing, because if, going back to here, up to here we're all good. We don't have to agree on why climate is changing, we just have to agree that it is. And that's a data issue. You look at the data, it tells us it's changing, we're all good. Here's the problem, though. If you're going forward into the future, why it's changing determines our response and the way we get our information. So that's why this issue is important. If we think it's changing due to natural causes, we're just going to use historical data because there's no reason to use anything else. We shouldn't use anything else. But here's the problem. If we think climate is changing due to human activities, then we cannot use historical observations as a quantitative guide to the future. We can use historical trends as a qualitative guide to suggest the direction of the change, but we cannot use them to get real numbers for the future because the future is going to be different than the past, because the future will be determined by our activities. So that's why we have to use physics-based climate models that account for human activities and their impact on the planet. Now, we can be a bit schizophrenic. I mean, I've definitely worked with engineers who are not on board with human-induced climate change, but who are using the climate projections that we generate. I think, in the interest of clarity, it's essential not to be schizophrenic. Because why are we using something that we don't think works? It's like, why am I taking this homeopathic medicine if I think it's absolute junk and it's not, it's expensive? That's what I'm talking about. I mean, this stuff isn't free. So that's why I think it's really important to have this information at our fingertips. It's important to acknowledge the fact that climate has definitely changed in the past. It's changed because we get different amounts of energy from the sun. It changes due to natural cycles, and it changes due to geologic activity. But climate scientists have been looking at these natural suspects, so to speak, for nearly 200 years. That's how long people have been looking at climate and about human impact on climate. And we have answers to these questions. So we can no longer get away with saying it's just the sun. Because if we look at the energy from the sun, the purple line, it was going up, but what happened? It's been going down the last 40 years. Well, temperature from the Earth, the orange line, has been going up. So it can't be the sun. We should be getting cooler. If it were a natural cycle, we know that natural cycles like El Nino are basically like a seesaw or a teeter-totter. I found out that there's strong regional differences between seesaws and teeter-totters. Quick show of hands. Who says seesaw? Not that many. Who says teeter-totter? A lot more. Who says something completely different? Anybody? You can tell me after. Natural cycles simply move heat around the Earth, typically between the ocean and the atmosphere, sometimes between the Atlantic and the Pacific, or the North and the South. So if our atmosphere were warming due to a natural cycle, where would that heat be coming from? I know it's after lunch, but I'll give you a clue. There's only 2 answers, and they're on the slide. It would have to be coming from the ocean. And we can look at the heat content of the ocean. This is the increase in the heat content of the ocean in exajoules. I like to measure my calorie intake in exajoules. It lets me eat all those cookies for lunch, and I feel really thin. The ocean is actually absorbing 20 times more heat than the atmosphere, the land, and the ice put together. So when we look at global temperature change, we are literally, not figuratively, literally looking at the tip of the iceberg of global warming. That's why it can't be a natural cycle. Now, there are some natural cycles that are external to the Earth's climate system. These are the orbital cycles, the changes in the Earth's orbit that drive the ice ages and the warm interglacial period like we're in right now. So some people will say, okay, well, it's not like El Nino or a natural cycle inside the Earth system, but isn't it just the fact that we're getting warmer after the last ice age? I blame the movie that everybody's seen if you have kids, the movie with the squirrel with the nut. Everybody now knows that we had an ice age and we're still getting warmer. Well, here's the thing. Number one, our carbon dioxide levels are way outside the ballpark of any cycle that we've seen over the last 800,000 years. You can take this back a lot farther. Number two is, if you zoom in on the last few thousand years, which kind of cover the development of our society, of widespread human development, what has been happening over the last few thousand years? Our temperature was actually on a slow downward trend. Until the Industrial Revolution. In fact, a paper came out last year, which I think is one of the most important papers that nobody ever talks about. It was a paper where they actually calculated that, according to our orbital cycles, we should be expecting the next ice age. And it concluded that we have indefinitely delayed the onset of the next ice age because of all the carbon that we've been pumping into the atmosphere. Now, that's a good thing because the next ice age would pose a significant challenge to infrastructure. So I'm not an advocate of letting that go. I think it's good that we've postponed the next ice age, but we've gone a little too far in the other direction. And just in case whoever you're talking to says, okay, well, it's something we don't know yet. Well, guess what? There's a paper on that too. Bruce Anderson published what I think is a genius paper. He asked, what if it's something we don't know? And the thing is, if it's going to be something we don't know about, we have to account for all the other things we do know about. And when you do that, he concluded that there's no way that any more than 25% of the change we've seen so far could be due to something we don't know about. So if our climate were changing because of the sun, we'd be getting cooler. If it were changing because of natural cycles, the whole planet would be warming. The whole planet is warming. That's how it can't be a natural cycle. Otherwise, our heat would be coming from the ocean. And it can't be the Earth's orbit because the next thing coming is an ice age. The fact of the matter is that ever since the Industrial Revolution, we've been producing a ton of carbon. That carbon is building up in the atmosphere, taking something that is natural, our natural greenhouse effect, and adding to it. I don't like to use the word enhanced very much because enhanced actually sounds kind of good. Like, what if I enhanced your bank account? What if you enhanced your students' grades? That's one of the challenges we have is the language that we use. And the bottom line is when we look at real temperature and we look at what all of our physically based models say our temperature would be on a planet with no people, we cannot explain the last 50 years. To explain the last 50 years, we have to include human carbon emissions. That's the only way we get a warming. This is not some brand new science. These are the old dudes who actually invented this stuff. The first climate modeler was the guy in the middle. 1890 was the first climate model, calculated by hand. And I really love this graphic because it links climate with engineering. Isn't this perfect? The fact of the matter is that 97% of climate scientists agree that humans are the primary cause of our warming. And what if 97% of engineers agreed that the bridge would collapse? Who would you trust? That's really kind of the bottom line. One of my favorite websites is Skeptical Science because it answers a lot of the questions people have, including, is it warming on Mars? But back to our topic. That's why it's so important to be clear about the cause of our warming. because otherwise we're not going to know how to ask for the answer. So what does the future hold? Well, I was talking about uncertainty, and I'm going to go back to and conclude this section with uncertainty. Our future projections are uncertain, but here's the thing. We know what the sources of that uncertainty are. Our future is uncertain because of natural variability. Natural variability, just to remind ourselves, is the wiggly line right there. That's our natural variability. So we know the future is uncertain because of that. But we also know that the future is uncertain because our climate models are not perfect and never will be. And the future is uncertain because it depends on the choices that people make. And we cannot predict what people are going to do because people do not follow a normal distribution. If we could predict what people would do, we would not need the NSF or any other funding agency because we would be out making billions of dollars on the stock market because we could predict human behavior. Wouldn't that be nice? Unfortunately, we can't. So how do we address these sources of uncertainty? The first one is actually not that hard to address. Whenever we look at climate projections, we have to make sure we're using appropriate timescales. What is an appropriate timescale? Let me give you an example. We hear a lot in the news about global cooling, how the Earth's temperature is not warming anymore. When you pick little short segments, when you sample from the Earth's temperature, you can make it do almost anything you want. I think I could seriously make global temperature play Mary Had a Little Lamb if I picked the right data points. The reality is that climate is the average conditions over at least 20 to 30 years. And so when we're looking at future climate projections, we need to make sure we're looking over appropriate timescales. We can certainly look at variability within those 20 to 30 years, but when we're looking at a change, we have to make sure we have a long enough sample. How do we address the fact that our models aren't perfect? We could have a whole week on this, but I'm going to give you the one short answer. You use a bunch of them. Long answer, you spend 2 years of your life trying to figure out which models are best for a certain area by looking at the dynamical patterns of the models. I don't recommend that unless you literally do have 2 years of your life and you are trained in atmospheric dynamics. If you do not want to do that, thankfully, research has shown, peer-reviewed research that can be cited, that if we just use a bunch of models, we'll end up pretty good. So what do we do? Just to give you an example, this is showing projected changes in temperature for the state of Delaware. We recently did a climate impact assessment for Delaware. We use a bunch of models that are lower sensitivity. In other words, when you give them a certain amount of carbon emissions, they warm by a lesser amount. Then we add a number of medium sensitivity models, and then we top it off with some higher sensitivity models. All in all, these cover the accepted range of projected climate sensitivity. There's many other things, again, that you could get into here, but bottom line, back of the envelope, this is the best thing that we can do. Lastly, our future scenarios, human choices. What if we continue to depend on fossil fuels as our primary source of energy? What if we transition in a sensible and sustainable way to alternative sources of energy that do not produce carbon? The different colors here are the different scenarios, and the shaded area around it is the uncertainty due to the climate models or climate sensitivity. So you're actually looking at scientific uncertainty and scenario or human uncertainty in the same figure. When I'm only looking out 10 to 20 years, what is the most important source of uncertainty? Number one. When I'm looking out 20 to 50 years, what is the most important source of uncertainty? Number two. When I'm looking out past mid-century, increasingly, number three becomes more and more important. So the source of uncertainty that matters the most to us depends on our planning horizon. It's not a scientific question. It's a practical question. So how do we get this down to like an individual weather station? And that's a lot of what we do. We take these scenarios, they go into a global climate model, and then we take the output from the global climate model and we run it through a downscaling model that incorporates either observations or higher resolution physically based modeling. There's two different types of downscaling. You can do both, or you can do one or the other. And then from that, we develop projections for individual locations, weather stations or a high resolution grid. What type of information can we get out of this? Well, we can look at, for example, the number of days per year over 100 degrees, or 105, or 110, or whatever threshold matters. In the past, where I am in West Texas, we only get 9 days a year over 100. Everybody thinks Lubbock's so hot. It was only 9 days. But in 2011, we had a summer with more than 50 days over 100. And that is what we expect to be the typical summer within a couple of decades if we continue on our current pathway. If we continue on our current pathway even further into the future, we expect it to be much more extreme. This is under the higher scenario. These are projections I did for the last National Climate Assessment in 2009. We also expect, as a general pattern, that areas that are already quite wet are getting wetter and areas that are dry are getting drier, but we also expect extremes to increase. So we have a paper that just came out a little while ago. Let's try to get this here. There we go. We have a paper that came out, I think, a couple weeks ago in Climate Dynamics, where we looked at drought as measured by the Standardized Precipitation Index. That's the top figure. That's looking at the change in summer drought as the world warms by 1, 2, or 3, or 4 degrees. The world, not North America. The bottom is looking at the change in variability. This is interannual variability, but you can also look at daily variability. And what we see from many places is a big increase in variability also. And that is, again, consistent with what we see happening around the world. We've done things like, for the city of Chicago, they had a really bad heat wave in 1995. So we actually captured the exact meteorological characteristics of that heat wave for Chicago, and we estimated how frequently we expect it to recur in the future. These heat waves are no joking matter. In Chicago, it was responsible for about 700 deaths. A similar but longer heat wave in Europe in 2003 was responsible for 70,000 deaths. That's 70. For Delaware, just for example, we looked at the increase in heavy rainfall events for individual locations, and we saw a really interesting gradient where right now heavy precipitation is stronger in southern Delaware as compared to northern, but in the future we expect greater increases in northern Delaware as opposed to southern, and that's important information for them. In Chicago, we looked at the frequency of days per year with more than 2.4 inches of rain. 2.4 inches is not a scientific threshold, it's an infrastructure threshold. They're really concerned about combined sewer overflow. They're also very concerned about the Chicago River flowing backwards into Lake Michigan. Why would they be concerned about that? Pollution and international problems. There's the International Joint Commission on the Great Lakes. Lake Michigan connects to Canada. If they flow backwards into the lake and that pollution gets to Canada, there are serious issues. And last time we were at war, we burned the White House. In Chicago, we actually worked with a risk management firm to go through 18 city departments. 14 of those city departments identified thresholds or other vulnerabilities to climate or weather patterns that we could put dollar signs on. I remember the first time we met, the mayor basically forced everybody into the room, and you could tell that nobody really wanted to be there. You know, the Department of Emergency Response was like this. The Department of Parks and Rec was eating their banana. And everybody's kind of like, why are we here? In the end, like I said, 14 out of 18 departments found ways in which they would be affected by a changing climate that they could put dollar signs on. During extreme heat, the south side of Chicago goes crazy in terms of emergency calls. Parks and Rec is now, when a tree dies, they don't replant it with the same species, they plant it with a species that's native to 200 miles further south. They're redesigning, again, their storm sewer treatment, and they're looking at redoing the way they get their energy to look for greater cooling and less heating costs. So if you want to play around with any of this data, it's available on a USGS website that was partly supported through the Climate Science Centers. And you can download this data in terms of county or in terms of HUC or in terms of all kinds of different ways, as well as just gridded. If you Google climate projections, we're on the first page of Google. That's always a way to measure your success, isn't it? Just Google climate projections in USGS, and this will pop right up. So lastly, to close, what can we do? This is really up to you guys. It's not up to us climate scientists, but from what I've seen, I think there's some hopeful things we can do with this information. We can redesign our drainage systems if we're expecting more heavy precipitation. We can redraw our flood zones if we're expecting more flooding and sea level rise. We can design more weather-resistant materials if we expect to see greater stresses. Sometimes we don't. We were doing a study for Boston Logan Airport this past year, and they wanted to know if we would reach conditions at which their asphalt might start melting like it does in Phoenix. We did the projections, and we concluded that no, they are not going to see those conditions even under a higher scenario. So they do not have to plan for that. If you're looking for resources, the National Climate Assessment is a great resource to look for the trends, both observed and projected. And there's also a lot of information out there on customized assessments, this being the one that we did for Delaware. Bottom line, though, I love this picture. The bottom line is that climate is changing, and by preparing for change, we'll be okay when it happens. I love this picture, even though it's far away from here. In Holland now, they're designing floating villages. Why are they doing this? Because if sea level rises a foot, what will they do? They'll put out an extra foot on the anchor chain. Whoop-de-doo. That's the situation we want to be in. Heavy precipitation increases 50%. Whoop-de-doo. We're already prepared for it. And I believe that's what we can do. Thank you.
So we have time for a few questions. Oh, come on.
Everybody's still digesting.
Well,
So it looks like one of the things we should do as engineers is cut down on use of cement. I saw you had a big chunk of in your carbon emissions there.
That's true, but MIT has just invented, I just read this week, a new way to process cement that radically reduces the carbon emissions. So I think that that's a good example of how we can still do the same things in smarter ways. Yeah, but you got sharp eyes.
I couldn't see what percent. But
I'll take us back. Here we go. It's small, but it's not insignificant. Yeah.
Wasi?
You mentioned that you studied for a CD that whether you reach a condition that asphalt melts. So what type of study did you do? Like, can you elaborate on that study a little bit?
Sure. Let me go to the slide that kind of describes our methodology. Here we go. So what we specifically do is we develop high-resolution climate information for the locations that people are interested in. If a certain system is usually designed based on climate normals from certain weather stations, we develop climate projections for those weather stations. If it's designed using more of an aerial average, then we develop projections for an aerial average. Then, and this is really important, we work together with the managers and the engineers who understand the performance of the materials. Because as a climate scientist, I know almost nothing about the performance of the materials. We need to get the information from the people who have that as to where are the vulnerabilities in the system and the materials and the infrastructure. And then that comes back to us, and we develop projections specifically of those thresholds, if there's certain thresholds, or if there's certain frequencies or intensities of temperature, precipitation. We've even done other things like ice storms, nor'easters, things like that. And then we give that information again back to the engineers, and then they assess how that might change their maintenance or their future planning. So it's very much an interactive process where we go back and forth together multiple times in order to make sure we get information that works.
So in a sense, actually, if you look at this, that we have just utilized for, a lot of industry and, big homes, heating, cooling, all of these, comfort. And then we see that we are leading to a unsustainable type of situation. How do we actually balance this? Is there really any way to do it acceptable way? Is there? I think it's a very complicated problem. We all know that something is happening, but how do we actually tackle this? I don't know. What are your thoughts?
I think that you have just hit the nail on the head in terms of the problem we're confronting. If climate were changing 1,000 years ago, and we lived in a bunch of tents, and sea level were rising, or hurricanes were getting stronger, or drought was getting more frequent, we'd pick up our tents and move. The reason why we care about this problem is because of our infrastructure. We can't pick up 2/3 of the world's biggest cities and move them away from sea level rise. We can't pick up the whole farming industry in the Southern Plains and move it somewhere else. I believe, I don't know, but I hope that by looking at this future information, we will be able to develop ways to plan such that the infrastructure we build today will be able to withstand the conditions of tomorrow. There's no doubt that some of our infrastructure along the ocean front will be abandoned. Some of our agricultural practices will have to be left by the wayside. But I think that it is possible for society to prepare if we do so now. I kind of think of it like going to the doctor and being told that your arteries are 15% blocked now. If we wait until we're on the operating table waiting to get our chest cracked open for bypass surgery, it's too late to do anything about it then. But if you're told now, we have a chance through diet, exercise, lifestyle, we have a chance to plan for a different future. And so I don't know how to do it. I feel like that is why engineers are so essential to our future. But I think that we can if we take this information into consideration. And rather than driving down a road looking in the rear view mirror to tell us where we're going to be in the future, we take our eyes off the past, we look down the road, we say it's going to be quite different. There's going to be some hills and dips and curves. Let's plan for those so that when they happen, we'll be okay. I'm sorry, that was a bit of a vague answer, but I think it's a really important question. Yes, maybe one more, or are we done? Oh, okay. All right.
So based on the sources of uncertainty, it seems like right now engineers can design comfortably out to 50 years. But to really design out to 100 years is where we really need to see what society is going to do. So I guess the question is how long do we have until that really has to be determined so that we can make reasonable designs, up to those time frames?
That's why this is, well, first of all, if we are designing at 50 years, we still need to take into account the scientific uncertainty and climate change.
Right.
Because climate is going to be different. That if we go back to that wiggly line there, that line will have already tilted in 50 years.
Okay.
But in terms of scenarios, when we go out long term, what I prefer to do is I prefer to look at the changes we expect under a higher versus a lower scenario.
But you had those two curves.
Yeah, exactly. Because it's really a judgment call. I mean, the lower is what we're going to have to adapt to pretty much no matter what. I mean, it's going to take a miracle to be any lower than the lower. I'm open to miracles, but I'm not going to count on them. The higher is what we can avoid by reducing our impact on climate. So in a sense, it serves as a motivation if you say, look, we can't design infrastructure to cope with this under certain situations. People need to know that so that we make good choices today. So that's tough because it's not a science choice, it's not an engineering choice. It's a value choice. What scenario we think is going to happen. Yeah, tough.
Can I ask one question?
Sure.
So actually, in your presentation, you've shown urban flood is a kind of concern actually, in future. I mean, it's urban. When I say urban flood, the flood in the city. Okay. So now you say, okay, maybe in future, based on these extremes, we need to design the sewage pipe with a higher depth. But on the other side, ice is melting, sea level is increasing. But where this extra water will go? So I'm just a general question to an environmental or a climate scientist. So do you also or a group of you also bring this move away from the seafront or go to some other places where altitude is higher? So is there kind of movement started or what do you think?
Well, we should advertise for the Southern Plains, Oklahoma, North Texas. We look good. Yeah. I'm actually letting the insurance companies do that. Insurance companies are getting to the point where they don't want to insure people anymore. There was a big deal where Allstate didn't want to insure people living in Long Island. Farmers Insurance sued the city of Chicago because they said the city knows that heavy rainfall was increasing and they didn't make preparations for it, so Farmers Insurance was paying the bill. I think, though, the bigger picture that your question raised is, again, a really important point, and that is that people often say, well, what's the biggest reason we care about climate change? The biggest reason depends on where we are. The ways that we are already vulnerable today are the ways that climate change will hit us in the future. Our Achilles heel today is where we're going to get bit in the future. So in other words, if you're in Houston, you're going to get bit by sea level rise and stronger hurricanes. If you're in Oklahoma City, you will not get bit by that. In fact, you may benefit from people moving in and boosting the local economy. But we will get hit up here by our droughts and by our heat waves. So that's why these regional studies are so important, because we can't make a blanket statement about why climate change is important. It matters where we are. Literally, if we are in Dallas versus Houston versus Lubbock versus OKC, that matters in terms of how climate change affects us.
One more quick one, and then we'll move on.
One thing that I've noticed, there have been some news reports about evidence of possibly permafrost melting and the methane contributing to this in a more serious way than carbon dioxide. Can you comment on that a little bit?
Oh my gosh, yes. Very briefly, I was actually asked for the New York Times. I'm pulling this up not because it's my office hours. See, no office hours tomorrow. I am in OKC. Actually, Norman, I'm sorry. Yeah, exactly. You see my travel plans. Here we go. This is the picture I was looking for right here. There we go. I was asked by the New York Times last week what is my biggest fear as a climate scientist. My biggest fear is the danger of the Earth responding to our warming in ways that we do not have in our climate models. One of the biggest things we don't have in our climate models is the fact that there are massive amounts of methane trapped not just in the permafrost. There's massive amounts of methane trapped in the continental shelf in the Arctic. 5 years ago, I wrote the chapter on geologic methane sources for the EPA's Natural Methane Report. When I did that, I did a full literature review, and there was not a single published paper suggesting that geologic methane would ever leak out of the continental shelves unless the ocean dropped by 200 feet, which would release the pressure on the methane, and then it would leak out. Fast forward 3 years, and 2 different studies, one Russian, one American, have documented that methane leaking out of the continental shelf in the Arctic. Now, it's because the water's warming so fast, it's melting it. It's preserved in a ice-like lattice structure, and that ice is melting. Now, the methane in the continental shelf has not yet made it into the atmosphere. It's still being absorbed by the ocean, so we're still okay. But if it started to just bubble out of that continental shelf, I mean, I would be the first one in line asking Chevron to pipe it out and burn it. Because methane is 25 times stronger greenhouse gas than carbon dioxide. So this type of thing right here and this type of thing right here, this is kind of what keeps me up at night. And this is not in our models because we scientists tend to be quite conservative. We are conservative in the opposite way of engineers, I have learned. What does an engineer do to be conservative? An engineer takes the worst case scenario and multiplies it by what? 10, 4, 3, people give different numbers. What does a climate scientist do? We take the worst case scenario and we divide it in half. So just FYI, climate scientist conservative is exactly the opposite, and you got to take everything we say with a grain of salt in the other direction. Thank you.